In this video, I will show you something that I think is quite beautiful and extremely useful when you're visualizing it in 3D, and it's called the octahedral shear surface or shear envelope. And the octahedral surface is this in 3D. I'm looking for this point, this octahedral point. Now, why are we interested in such a surface? Well, primarily for failure theories. So people, especially soil scientists, use this octahedral surface for the sole reason of establishing what is the shear on that surface. And that surface is very specific. It's 45 degrees about one axis and 45 degrees about the other axis. So it's a very specific surface with that 45-degree normal shooting out. And I know I can find the normal stress, and I want to find the shear stress on that plane. And if that shear stress on that plane, which we call tau octahedral, if that shear stress is beyond some experimentally obtained limit, then we say the shear will begin to fail and through sliding, right? So the 3D octahedral surface is super cool, but how do you get it? It's really a 19th century construction coming from this triple Mohr circle. Once again, just to show you the visualization, you have a normal, but it's not arbitrary. It's very specific. Theta for us will be 45 degrees, and phi for us will be 45 degrees. This picture over here is for general theta, not 45 degrees. Remember, you have to go 2 theta on Mohr's world and 2 phi on Mohr's world. But for us, the theta and the phi will be 45, which means that these will be 90-degree angles on Mohr's world. Okay, how do we do it? Well, I have all the steps here, but before we get to the steps, we have a few other things just to remind ourselves about the stress, principal stresses. So this picture here is based on principal stresses. On this cube, for the octahedral shear stress, we will look at the principals, not the originals. So we have to start with the original stresses and then get the principal stresses. And then we will plot them. The first principal stress, which is 3 o'clock, the most positive number will be here. The worst negative principal stress will be 9 o'clock, it will be over here. And the third one will be in between these two. Recapping on how we do that, the problem would be to start with an original stress matrix. It doesn't matter what your stress matrix is, but you have to start with something. And you want it to be flexible enough that you could rapidly enter in the data. So I mentioned this in the previous video. You could enter it in matrix form here, or you could enter it in what I'm going to call scalar form here. Just type these numbers in, and then if you do the latter, type these numbers in, then your sigma matrix would be just pulling in these values. Or you could type it in here and then pull out the sigma. So what I did was you could see it. This matrix is built up of 9 individual numbers. So I found that to be easier. Then you do your principal stresses. So how do you get that? 2 ways. And we talked about that in a previous video, but the steps are here. So we start with this problem where sigma is your variable and you're just trying every imaginable sigma and you're waiting to see where does the left-hand side of this equation cross 0. So that's one way of doing it. I do want you to do that. I want you to plot this function, and this function is a big loopy, it's a cubic. But where it's crossing 0 is what I'm interested in. But I did not generate these surfaces based on that cubic. What I did was I generated these surfaces based on these cofactors. So that's the A1 matrix with the Q value, the R value, and the S value. And that is described in course pack 5, as are the invariants. The invariants, recall, mean that it is a set of 3 numbers based on stresses that are independent of the coordinate system. So any XYZ coordinate system will have the same three I1, I2, I3, which is why they're called invariants. Here's my setup for how to get the invariants, and then here's the R value, the Q value, and remember these are the fun ones with the 2/27ths and all that. And then we get the second method. Now in that second method, which I want you to do also, you get three values. You get sigma A, sigma B, and sigma C. They can come out in any order. But what I want to do is rank them according to the most positive. Even if they're all negative, I still want the most positive number. Or if they're all positive, I want the most negative number for the 9 o'clock. So that's why they're called sigma A, sigma B, sigma C. They just come out as they come out. So here's the first one, etc., etc. So then you have to manually rank them. So what I did was I plotted these points and I said sigma 1, for instance, is sigma A because that was the biggest one. But sigma 3 here is sigma B because that was the worst negative. So I manually did this. I didn't have the robot do that. And that gives me the circles. Now these three circles are really fun for one more reason, because given this original state of stress, it's literally impossible to say what is the worst normal stress and what is the worst shear stress. And now I get them immediately. I see it's 100 for the worst normal stress and negative 60, but I would say 100 is the worst normal stress. And then the worst shear stress is 80. And it's impossible, like I said, to intuit that from the original stress matrix. So this picture is really nice in that it gives you these immediate peaks, the 12 o'clock and 3 o'clock, or 12 o'clock and 9 o'clock. Now there's one more kind of beautiful thing which I never noticed before, and it's this thin green line. This is the base of the octahedra, which shows up here in 3D. So having the ability to do this, and GeoGebra is the way to do this, I think, I'm sure. I mean, I think this would be hugely painful to do in MATLAB, but I could be wrong. This kids program can handle it. And I also plotted the sigma and the tau nets, but I don't need those right now. I need these special ones at 45 degrees. So how do we do that? Well, this technique is actually general for really any angle, but we're going to focus only right now on, like I said, 45 degrees for the phi and 45 degrees for the theta, giving us 90 degrees in Moore's world. So I'll show you how this works, and this is super cool. And remember, also I said that you could be anywhere in this interstitial area between the circles or on any perimeter. Those are allowable, those are actual possible stress states. But even within this stress state, you might be exceeding what your material can handle in shear experimentally found. So that's the whole purpose of this octahedral stress diagram. So the graphical solution is crazy cool. It's a 19th century thing. I have the steps here for you, which we covered a little bit already. Find sigma 1, sigma 2, sigma 3. We just did that. Now draw the three more circles. The first circle is centered on sigma 1, sigma 2. So here's circle 1. It's going from 1 to 2. And then the second circle goes from 2 to 3. From 2 to 3, there it is. And so it's baby bear, mama bear, and papa bear. Papa bear is the biggest one here. So that goes from 1 to 3. So papa bear goes from 1 to 3. And then it's very quick in GeoGebra to get the centers of each of these circles. There's just a little midpoint button. Like, what could be easier than that? So get the three midpoints, the midpoint of the first circle, the midpoint of the second, and the midpoint of Papa Bear here. Then we do this step here where we are going to draw 45 in the real world, which is 90 degrees in Moore's world, 3 through C1. So this angle will be 90 degrees through C1. So how do we do that? Well, you know, obviously it's super easy, right? In this program, it's super easy. Oops. Here it is, perpendicular line through C1. And perpendicular. Let's just leave it at C1 here. And then the next step is to find B1, which is the intersection of that line with circle 1. So there it is. It's at 12 o'clock. And then we go from B1 to sigma 3 with a circular arc. We go from B1 to sigma 3 with a circular arc. This circular arc is centered somewhere on the x-axis. So if you're doing this by hand, and you certainly can do this by hand, I'm not saying you can't, you'll have to put your pointy edge of your compass somewhere on this line, and then you will have to move your compass, adjust it until you have a circle going from B1 to sigma 3. Here in GeoGebra, it's pretty quick. Well, first of all, I need a point, so I'm going to put I'd like to have a big visible slidey point, so now I'm forced to be on that axis, and I'm going to go from B1 to sigma 3 with my circular arc. So it's saying, hold your mouse there, select the center and the 2 points. So here's the center, and there's 1 point, and there's the other point. Obviously, I'm not on that point right now. You could see the arc, but I will move my slider to make it fit. It also depends on which way you draw the arc. So just, if you're drawing it the wrong way, just start with the next point. And just move your slider until, boom, right there. That looks, oops, that looks pretty good, okay? The next one is our second one, and that's going from B3 to sigma 2. We went from B1 to sigma 3, and then from B3 to sigma 2. So we're covering all these interior things. So just one more time here. We could change the color if we want. And that will be going from B3 to sigma 2. So one more circular arc. There's my center, B3. And here's a good example. It flipped the other way, so I'm going to go this way. So there's my center from sigma 2 to B3. Okay. And then I just move this until that works. That looks pretty good. And where these two intersect, boom, that's the answer. That is the normal stress and the shear stress on that 45-degree surface. And like I said, this technique should work for any angles, but we're only going to do it right now for the special angles where these two intersect is the answer. And you could do this graphically just with your, looking at it. If you're on the computer, boom, it's pretty easy. And that number, we're just going to call that G. And I'm going to show you the name and the value there. So it's 26 on the normal and 66 on the shear. 26 on the normal and 66 on the shear. So then what I did was I went down here and I got a point and I called it octahedral point. And look how I programmed this. I said it's the x of this. I guess I should have called that octa h. I guess I called it octa h in the. Let me just make sure. Yeah, there's octa h. So I called it octa h. I just called it g here to match the other one. It's x of g or octa h. Then it's x of octa h again because I'm drawing this in 3D, and then the z-coordinate of the octahedral point is the y-coordinate of the 2D. Yeah, that's pretty cool, right? So let's take a look at that. So let me hide the circles here so we get it a little bit cleaner. And hide, and there's my arcs. So there's my octahedral point, and then what I did was I drew a normal from the origin through the octahedral point. So where's my origin? I think that's my origin, right? All right, so I'm going to draw a line from the origin through the octahedral point, and then I created that surface which you see is perpendicular to that. And then when I said the positive negative thing, I just I drew this plane. So I'll show you what I did here. I drew a plane perpendicular to that surface. So select a point and a perpendicular line. There's the point and there's the perpendicular line. So that plane is perpendicular. And then what I did was, think of this like our earlier lessons. This is the oblique plane, and then what I did was I just turned on the axis and I figured out where did this intersect, right? Where did this intersect? So this is like, remember the 3 dots that we did earlier? The 3 dots, where does it intersect? The y, the x, and x, y, and z. And then I just drew a triangle. So it's crazy cool. I want you to do this, at least by hand, but man, it would be so fun to do this on the computer. If you have a better way of drawing all this than GeoGebra, let me know. But man, what could be easier than this kids program that teaches 3rd graders and teaches graduate students equally as well? I think it's amazing. So congratulations on that, and see you soon.